My home university was not involved at all.
Compared to my first thought. I know, I'm sorry about that. But it's not you. It is literally trying to contribute something.
Just my salary from my master's. It's a bit sad.
All right, let's get started. Before reintroducing our speaker today, let me remind you of the events in the coming days. On Friday, we have a lunchtime talk at noon, given by Frederic Legg, right here, about what is called thinking in mathematics. Please join us for this lunchtime talk on Friday. Next week, we have a well-deserved break, so spring break, which I think we are all looking forward after a very intense first part of the semester. And right after the break, we are starting again on Tuesday, March 11, where Aniwa Dewey, who is our postdoctoral fellow, will be talking about a deflationary account of DCNN, so neural network-based models in visual neuroscience. Right after the break, also, we have a conference on the weekend of March 15 and 16, pragmatism and scientific measurement, with heavyweights coming to Pittsburgh. And Nancy Cartwright will be here. Hazard Cheng, I believe, I'm not totally sure, will be here. So it's going to be a very exciting conference. Please, if you want to join that conference, go to the website and you can actually already register. Not that you couldn't come if you hadn't registered, but it's useful for us to have a head count in advance of the weekend. And today it's my great pleasure to reintroduce Karl Hoefer. I had to do that last semester, and I will do it again. Karl is a senior visiting fellow at the center, as you all know. He got his PhD at Stanford and taught in many places, including LSE, Riverside, and Western. He's now in Barcelona, where in the group Logos, he's the director of the Barcelona Institute of Analytic Philosophy. And then I'm going to butcher the name, which recently became a Maria de Maestru Unit of Excellence, with funding from 2023 to 2026. He is the founding editor of the European Journal for Philosophy of Science. He works mostly at the intersection of metaphysics and philosophy of science, particularly philosophy of physics. He has published, as one said, and I think that's true in that case, in all the best journals, but I will only mention his recent book, Chance in the World, A Human Guide to Objective Chance, who won this year's Lakatos Prize. And Karl will be in London in a week from now to celebrate the prize, to give the Lakatos Award lecture, and to have a workshop on the book. I know it's as you all know, it's a tremendous honor to win that prize. Today, Karl will be talking about something a little bit different from what we talked last semester. In fact, very different. Kripke-Putnam essentialism about water and the laws, powers debate. Karl, floor is yours.
Thanks, Edward. Why am I talking about something strange like this talk? I first gave this talk, or something similar to it, in Athens in 2023, invited by Stathis Psilos, who was leading a research group there, doing a lot of work on the kind of stuff that I'll be criticizing in the second half of my talk. So I basically leveraged a paper that I had already written and added some new content, and gave the ancestor of this talk in Athens. And I was recently reminded that I also agreed to write up a paper based on that talk. And so that's my next writing project, and I'm looking forward to feedback from all of you to help me make that more useful. So let me get right to it, because I think I have too much to try to say. The plan of the talk today is going to be to, in part one, talk about this Kripke-Putnam idea about the essential nature of water, and why I think it's defensible despite it being one of the most ridiculed ideas among philosophers of science, as you'll see. although I will say that as I understand the thesis of the essentiality of the claim that water is H2O, it's less radical than some people initially hoped or feared. And then with that under our belts, in the second part, what I want to do is cast my baleful gaze at the dispositional essentialism literature, which is a part of the big revival of metaphysics that happened post Kripke. And I'm going to argue that that this way of doing the philosophy of nature and the philosophy of laws of nature in particular has overall been regressive and unhelpful. And I'll be looking at, in contrast, the way physicists talk about modal possibilities as a tonic or a better way to do things. Okay, so that's the plan. As I said, the background for this is something that actually even predates my education in philosophy, which is the Saul Kripke's naming and necessity, and the way that work opened a kind of a Pandora's box of acceptability to talk about metaphysical necessity back in amongst analytic trained philosophers. And with it, we had the revival of things like individual essences and kind essences and other monstrosities such as hexieties and quiddities, which coincidentally was the focus of criticism in one of my very first papers a long time ago. And all of this became discussed in analytic philosophy using the kind of rather primitive language of that we analytic philosophers tend to fall into, talking about things and properties. Ontology is listing the things that exist and maybe the properties, and using predicate logic or extensions of it into modal logic and so forth, which is a kind of a leftover or hangover from our logical positivist heritage. So that's the background. Now, how I got interested in recent years in thinking about this was by way of a provocative paper called Natural Kinds and Natural Kind Terms, Myth and Reality, by Søren Hagqvist and also Wigforss in BJPS, which was really provocative or triggering for myself and Genoveva Martí, who is my wife and colleague at Barcelona. Now, why were we triggered by this paper? Basically because in her case, Hagqvist and Wigforss attack the Kripke and Putnam idea about water and ridicule it like all philosophers of science do. And then they went on to say, and so, since Kripke's ideas are the basis of direct reference as an account of the reference of natural kind terms, we should just go back to being descriptivists, give that another try. And Genoveva has been convinced for her whole career that descriptivism as a semantic account of natural kind terms is just wrong and kind of hopeless. In my case, I've always been more or less convinced by, broadly speaking, the externalism that you get in early Putnam and Kripke, and also convinced that it's really important to maintain that in order to have a defensible understanding of how we refer to natural kinds, and that in turn is very important for defending scientific realism against some of the anti-realist attacks. So those were our motivations. Here's how Hagqvist and Wigforss characterize the Kripke-Putnam thesis. It's a version of semantic externalism, the thesis that extensions of natural kind terms are determined in the actual and possible worlds by underlying essential features of samples in the speaker's environment. The essential features for inorganic substances, at least, are typically assumed to be microstructural. We'll talk about what that means later. And these microstructural features, given the laws, help explain the observable and or stereotypical properties and behaviors of the substance. So that's the Kripke-Putnam thesis. And for both Kripke and Putnam, a paradigm example was the fact, which was discovered over the course of the 19th century and into the 20th century, I guess, that water is H2O. It's made up of molecules with this composition, two hydrogens and one oxygen. And Putnam gave the famous twin earth argument, which basically says, look, contemplate, we know that our world has lots of water in it, but now just imagine there's a faraway world in the galaxy that's just like our world, but really just like our world in every detail, except there is, where we have water, they have this other very complex molecule called XYZ, which is not water, but it plays all the roles that water plays in our world. And Putnam says and argues, if we imagine this to be the case, nevertheless, when we say water, we're not referring to stuff that's made up of XYZ. And when they say their word water, they're not referring to stuff that's made up of H2O. And the argument proceeds on the basis of intuition, but the intuitions convinced a whole lot of people and it became a very influential argument. Now, in philosophy of science, the Kripke-Putnam thesis has not been well received in large part, I think, due to it being considered simplistic when it comes to this talk of microstructure. And so there's been reactions against the thesis, which not only Kripke and Putnam, but that later Michael Devitt argued for in depth. And when it comes to biological kinds, John Dupre and many others criticized the idea that genetic or DNA structure is the microstructural essence of a species. And I actually totally agree with all the criticisms on the biology front. And when it comes to chemical substances, Hassek Chang, Paul Needham, and others, as well as Hagfuss and Wigforss, strongly criticized the idea that water is essentially H2O. And this gives you a feel for the tone of the criticisms. Kripke and Putnam were basically accused of acting like preschoolers with their thesis. So what do these people really, what's the basis of their objection? Well, they say it's a hopelessly naive thesis, which is not in tune with science. It's particularly wrong to say that it's essential to water that it's H2O. Why? Well, H2O is a composition formula, it's not even a structure, according to chemists. It just tells you the composition in terms of numbers of atoms of this kind of molecule. And there are lots of molecules, if you put the numbers of the different atoms there, you're not labeling a unique chemical substance because there are different forms with the same atoms. So if taken as a structure, it's misleading. Also because water molecules don't just sit there as nice whole H2O molecules, they link into polymer chains because of the way hydrogen bonding works. The molecules are constantly falling apart into ions and then reassociating. And the proportions of these ions vary with temperature and phase and other things. Then there's the complexity that there's ortho water and para water, which have really different properties, and it has to do with the spins of the electrons, and so on. And so there's no such thing, these philosophers say, as the microstructure of water, and certainly not H2O. Hassek says philosophers should follow the latest and best science as judged by scientists themselves, not some tired old approximation like water is H2O, which scientists who research on water have moved beyond a long time ago. It will not do to follow Putnam's notion, in itself 40 years old and already outdated even then, that the extension of water is the set of all wholes composed of H2O molecules. So that's what Hassek says. And I thought, dang, that's pretty strong criticism. Was Putnam really not aware of any of this? And then I looked at the original 1975, I think that's Meaning of Meaning. And there Chang actually lopped off the last part of the sentence, where Putnam gives us a hint that he knows there's a little bit more to the story, but it's not worth going into. And then I discovered later discussion by Putnam where he, well, as we'll see, he basically backs away from his essentialism, but he says this: assuming high school chemistry, water that isn't H2O may be conceivable, but it isn't physically or chemically possible. And then with a footnote, he says, I'll stick to high school chemistry because the actual quantum mechanical picture of the structure of water is immensely complicated. So Putnam kind of already knew that there was more to the story there, and that didn't dissuade him in the early days from the thesis. The way I see it, water is complicated, but it still has perhaps a disjunctive and imprecise microstructure. And so in the paper that Genoveva and I wrote, we say this: Kripke or Putnam might have said this instead of what they said. Yes, I won't even read through it. They might have given such a long, detailed description of the structure of water, but it was okay to not go into all that detail. What matters for the essence claim, I think, for the idea that's the core of Kripke's insight, that under given conditions, water always settles down into a fairly stable configuration that fits the kind of description that I just put up here. It's a natural kind. It occurs in nature, and it tends to always have the same sort of structure under similar conditions. We've discovered what that structure is, maybe not to the last detail, but we all know an awful lot about it now. And Kripke and Putnam just abbreviated this with microstructure. But secondly, and more importantly, look, they were not wrong. Being composed of mostly H2O molecules is what, given the actual laws in our world, makes water have this complicated microstructure and behave the way it does. That really is, as it were, the essence. As Robin Hendry, who also, like me, has defended the basic idea of the essentiality of this claim, he says, being composed of mostly H2O molecules is causally upstream of the stereotypical observable properties of water. I don't think causal has to be taken to literally here. And in a different paper on the same kind of topic, Hendry says, my proposal then is that water is the substance formed by bringing together H2O molecules and allowing them to interact spontaneously. And that they just settle down into a reliable structure with the reliable properties we know and love. In fact, even if you take a bucket of ortho water here and a bucket of para water here and just let them sit for a few hours, at the end, they'll just be regular water. Okay. So in my opinion, the lesson of twin Earths here stands. Having the underlying structure that it in fact has is essential to water. And so anything like Putnam's imaginary XYZ that has a very different underlying structure is simply not water, even if it has most or all of the surface properties we ascribe to water. Although I hesitate to point out that anyone who has spoken to chemists knows that no chemist thinks that this is even imaginable, really. It's not something that could be. And these truths, though, the truths up here, they held long before science revealed to us what the microstructure of water is and what the laws are that govern its behavior. In other words, this was true in the 1700s, as Putnam argued. Now, I do want to give a caveat here. I want to just set aside Kripke's thesis that water is H2O is an identity statement and hence true if it's true at all in all possible worlds. I think identity statements that you find in the wild are often ambiguous, context-dependent, interest-dependent, and they're not usually numerical or mathematical identity. They don't obey transitivity and so on. So I just don't like this move in general when Kripke or anyone else does it. We'll kind of see this again in a moment. So the claim I'm defending then in any world, nothing that's not mostly made up of H2O molecules is water. Now, what sort of claim is this, though? Because I already told you, it's not quite as metaphysically deep as some people thought. Well, in addition to the caveat I just mentioned, that it's not an identity statement, this claim, if it is true partly because of how we use language. I mean, that's just the way humans, in our broad thinking about natural kinds and the way we use language, and that's why as a semantic thesis, the Kripke-Putnam thing gained a lot of currency and is still defended by many philosophers of language. And so I don't want to say this is some sort of incredibly deep thing that has nothing to do with us, as it were, that it is independent of humanity entirely. It is partly due to how we categorize things and conceptualize things, but also partly due to nature itself. All right, now, as I said, Putnam retreats from the metaphysical claim, at least by 1990. And this is a quote that we should read through because it's going to be important. He says, "I don't think that a criterion of substance identity that handles twin Earth cases will extend handily to possible worlds. In particular, what if a hypothetical world obeys different laws? Perhaps one could tell a story about a world in which H2O exists. Hydrogen still consists of one electron and one proton, for example, but the laws are slightly different in such a way that what is a small difference in the equations produces a very large difference in the behavior of H2O. Is it clear that we would call a hypothetical substance with quite different behavior water in these circumstances? I now think that the question, what is the necessary and sufficient condition for being water in all possible worlds, makes no sense at all. And this means that I now reject metaphysical necessity." So that was Putnam. And I want to say, Putnam, hang on. Look, remember, my claim was just that in any world, nothing that's not mostly H2O is water. And in any world where water exists, it's composed mostly of H2O molecules. But even I want to say the following. If we imagine really that twin Earth exists, we imagine that in this world there's no hydrogen or oxygen. In fact, let's make it a different possible world instead of inside our world. Some utterly different kind of substance XYZ that behaves mostly like water behaves in our world. We might decide to agree that there are two substances in all of the multiverses that are water. As it turns out, although only one exists in one only exists in worlds with very different laws, the XYZ type of water. Although I have to say, I think this is unlikely to be the semantic choice we would make, even if we were presented with this choice and had to make it. I think more likely we would say that in this other alien world, there's a substance whose superficial qualities are much like those of water in our world. End of story. But okay, maybe we would have made the other choice. But in that case, we would have here in front of us a kind of a jade case where there's just two kinds of things that share the superficial qualities, but they're two different substances, and we understand that they are. And we would have made a semantic amendment to the reference in semantics of water. And here, coming back to identity, although a big bunch of XYZ is water, under our assumed usage would be true, and a big bunch of H2O is water, also a big bunch of XYZ is a big bunch of H2O would be false. They're different substances, and so they are so because of their radically different microstructural compositions. So here the is obviously not a transitive is. Now coming back to Putnam, he says, is it clear we would call a hypothetical substance with quite different behavior than water in all these circumstances? And he's imagining that we're modifying the laws of nature. And I'm agreeing with Putnam that no, it's not obvious. We might, but we might not. But that's a fact about how we use language. not necessarily something with deep metaphysical import. And I want to point out that also Putnam says in the next two sentences, I now think that the question, what is the necessary and sufficient condition for being water in all possible worlds, makes no sense at all. And this means I now reject metaphysical necessity. Here, Putnam calls into question whether there's a necessary and sufficient condition for being water in any possible world. But I just want to point out, I have not been maintaining that being composed of H2O is necessary and sufficient, only that it's a necessary condition for being water. And it seems to me that Putnam's counternomic scenarios do not refute this. It seems to me that what Putnam is doing here is equating metaphysical necessity with necessary and sufficient conditions. And I wonder if he's doing that because he's sort of doing what I think Kripke did, treating water is H2O as an identity statement and then applying the rules of modal logic. And more generally, the framework of extensional semantics. That's hinted at by the fact that he talked in an earlier quote about the extension of the term water. So I want to just now wrap up the first part of the talk and take stock. It seems to me that we've seen that this literature talking about the Kripke-Putnam thesis has made certain mistakes. One mistake is to move from a plausible essential feature of water to an extension determining kind essence, which is something like an individual essence, but for natural kinds. And I think that the idea that water is H2O as an identity statement played a role. And another mistake is to go from unease or uncertainty about how we would decide to use the term water in certain weird possible situations for decisive evidence against what I think is a plausible essentiality claim. And here I think that the idea that kind terms are predicates and predicates always have to have definite extensions in all worlds is playing a nefarious role. Okay, now to move to part two. What I want to do now is talk about modal physics, bring a little bit of, it's not exactly real heavy-duty physics, but bring physicists' own words about possibilities into the equation. And I'm going to use it as a weapon against this trend, which emerged over the last 40 years of doing philosophy of nature, using notions like powers and capacities, dispositions and propensities and stuff like that. Plus, while still using the possible worlds and modal and predicate logic tools from earlier generations of analytic philosophy. So I'll be criticizing this sort of whole trend, getting back to these notions in metaphysics. And early figures were my beloved supervisor, Nancy Cartwright, in her 1989 book, with the word capacities in particular, but she also really brought Aristotle back into the picture explicitly. Some Australian metaphysicians and other good philosophers, and more recently in the 21st century, Alexander Bird and others have jumped onto the bandwagon of using these tools, this language to talk about laws of nature and gnomic necessity. And there's a kind of a key goal that's shared widely in this literature, which is to argue for some sort of necessity in nature, physical necessity in a robust sense, but demoting the role that laws per se play in the argument, where by laws I mean the sort of things that you see in physics textbooks, the mathematical laws. All right, I'll come back to dispositional essentialism and the powers literature and so on in a moment. What I want to do now is go on a little detour about exploring modality in the physics style. And I got into this precisely because of that Putnam quote in his 1990 paper, where he speculates on what would happen if, you know, the laws of nature were just slightly different, but in a way that strongly affects the properties of water. And I started looking around, and then I bumped into a rather big literature which is out there, which involves physicists fiddling with values of parameters that are found in the standard model particle physics, and showing that you can get things like this: worlds in which water's freezing and boiling points are considerably higher or lower. Worlds in which H2O molecules exist, but they're much less dipolar, which would change water's chemistry significantly. Tweaking a little bit more hard, you can get worlds in which oxygen is too unstable to permit H2O molecules to form, and other things. If you fiddle, in addition, with parameters that are part of the lambda cold dark model cosmology, which for the past 20 some years has been sort of the standard big picture of the universe, then physicists argue that we can get worlds in which no atoms more complicated than hydrogen exist at all. They just never form. Worlds in which stable atoms with 16 protons exist, but they don't have any neutrons in them. And then the question arises, is that oxygen? Something that the physicists don't get, as far as I know, they never get anywhere near this. Worlds in which a complex XYZ molecule plays most of the roles that H2O plays in our world. No. It doesn't go anything like that. The physicists stick to basically the laws, broadly speaking, of quantum physics as they emerged over the 20th century, and they play around with details that seem contingent. So what are they interested in? These physicists exploring counternomic possibilities are usually, it comes from being struck by the fact that when you do play with a lot of these parameters in the standard model or in the cosmology, you find out that rather small shifts in the values of some of the constants or parameters make a universe completely inhospitable to the richness of chemical structures we find around us, and hence to life. And so this literature is now known as the fine-tuning literature. And it's exploring how all these parameters and constants seem to be fine-tuned to permit the richness of our world, and in particular, the emergence of life. It's very interesting, and even on physical grounds, there are some people who contest whether the fine-tuning is as incredibly precise as some physicists maintain. But in any case, they're mostly talking about rather nearby possibilities, at least compared to what philosophers like to do with their language. Just fiddling with parameters that exist in the equations we're already familiar with. And these physicists talk about the weak and strong anthropic principles. And I, unfortunately, I'm not going to talk about that at all. You can appreciate, as I do, that this is a very interesting literature full of really interesting speculations about the other possible ways physics might have been, without caring about whether this, says that there's a God, or whether it says we must be living in a multiverse. Forget all that. I think all those moves are argumentatively unsound. But the physics itself is quite interesting. And it's all just based on existing very long-standing physics. And they don't use modal logic or talk of essences, powers, dispositions at all. So when physicists talk about the contingency of the laws of nature, they do this kind of stuff. And the laws that they're working with are very, very hard to put in the form that philosophers for many years used to say the laws of nature have, either as universal generalizations or statements of necessitation. Now I realize that the more recent powers literature doesn't usually use this kind of terminology anymore. But it's almost worse. They're just using standard English. What they do in the more recent literature is basically try to impose a language of everyday experience of properties that possess powers and so forth, and impose that onto physics and physical law. So that's the end of the detour. What do these guys say? I'm going to give you the dispositional essentialist argument for gnomic necessity in a very oversimplified form. So don't take this as something that is representative of any particular person. The first move, I think it has a lot of plausibility to it, is to say, well, properties are identified, or their natures are basically tied up with their causal or dispositional profiles. In other words, what a property is the kind of stuff it does, the effects it has on other properties, on us, say visually or auditorily or whatever. And so to be, for example, a positively charged object is to have the power or disposition to attract oppositely charged objects and to repel like charged objects in a certain way. Which way? Well, it's the way that Coulomb's law captures. And so the move now is to say physical laws like Coulomb's law and all the others simply capture in a mathematical way the powers and dispositions of the natural properties that exist in our world. So far, so plausible. But this has a surprising upshot, which is that when you say, oh, but I can imagine the world could have had completely different laws of nature, you have to ask yourself, what are you really imagining? If you imagine that positively charged things attract other positively charged things, is that a real conceptual possibility, or are you just making a verbal mistake? And they think it's the latter. They think that, well, if you try to imagine a world where positively charged objects do different things, you're really just imagining a world with completely other sorts of properties, alien properties, and not the properties that we find in our world. Therefore, the physical laws that we've discovered in our world are actually necessary truths, because in any world where all and only the properties found in our world exist, the laws of nature are the same as in our world. So that's the kind of general thrust of the argument. First observation is that in this literature, the examples that are almost always trotted out to illustrate the view are almost always from 17th to 19th century physics, and in particular, it's almost always either Coulomb's law or Newton's law of gravitation. Very occasionally, you'll get some 20th century examples appearing, most often from chemistry or simple atomic physics, where talking in terms of powers and dispositions seems quite natural, like when you say that water has the power to dissolve salt due to its dipolar nature. But detailed mathematical forms of laws and equations are almost always left off stage, and they don't play any significant role in the discussion. Second observation about this literature. It seems to me that the quantum physics that unfolded in the first half of the 20th century really very hard to cast into this talk of powers and capacities and dispositions. Why? Stable atomic configurations, that was one of the triumphs of the early 20th century physics, understanding why atoms can be made of positively charged things and negatively charged things, and they don't just collapse into unity with each other. Well, all of that is dependent on Schrodinger's equation, and Schrodinger's equation looks not at all like a codification of some particular properties, powers, or dispositions. This doesn't look like that. And the very particular shapes of these electron orbitals play a huge role in everything to do with chemistry, and in particular the chemistry of water, for example. Another feature that makes atoms work the way they do is, of course, the Pauli exclusion principle. So that you have these different orbitals with their different shapes because electrons can only two electrons can occupy an orbital at a time. But the Pauli exclusion principle is really only badly expressed like this. Electrons and other fermions have the strong disposition to not get into the same state. No, it's not that. It's a symmetrization requirement on wave functions. That's what the Pauli exclusion principle actually is. Continuing with this kind of observation, it seems to me that when you bring in the strong force, which holds nucleons together in the nucleus, you get something that's even harder to understand because you get this weird shape where, depending on distance, it's either attractive or repulsive. But now, in virtue of what property do we have these dispositions of attraction or repulsion? It's not clear. Before we were talking about dispositions because of being charged or because of having gravitational mass. Here it's not so clear what bears the property. And then we get to nuclear decay or neutron decay. If things have this disposition to bind, why do they fall apart? Well, mathematically, it's easy to explain because everything has to be a solution to the Schrodinger equation, and there's quantum tunneling and things like that. And it seems to me that when you get to full-blown quantum field theory of the standard model, you get the coup de grace to the idea of imposing the language of powers and dispositions on 20th century physics. Why? Well, the things that exist, and that whenever the philosophers talk about this, they almost invariably talk about particles. Well, most physicists say that they turn out not to even to be fundamental. They're just excitations of the real fundamental thing, which is a quantum field, various kinds of quantum field. And the properties of quantum fields, what are they? Well, they're not charge and mass and things like that. The properties of quantum fields are dispositions to take on mathematical forms that are solutions to the Euler-Lagrange equations for a certain only mathematically describable action. And so what remains of dispositional essentialism when you try to put it over the standard model is this. It's the essential nature of the quantum fields to behave in accordance with solutions of the Euler-Lagrange equations arising from the action as follows. Here's the action. Okay. By the way, every picture and everything in this talk is mercilessly stolen without credit from the internet. I promise to do better when the written version comes out. So this has two problems. The first problem is a kind of a triviality, because what I had in the last slide comes close to being a mere prepending of it is the essential disposition of the fields making up physical reality to in front of the physical equations that the physicists deal with and where the real action is, according to Planck. On the other hand, at the same time, it's an overly strong necessity. Despite being kind of trivial, it's also overly strong. Every detail then of the standard model, including the values of every fundamental constant or the ratios of the constants, to the last decimal place then becomes metaphysically necessary. And if you tweak anything, oh, well, then you're talking about a world with completely different entities and different properties. That's not a very plausible way to do modal metaphysics either, I think. And we can contrast this with the way physicists do their modal speculations in this fine-tuning literature. Now, as I said, the bulk of the literature is just trying to explore what would go wrong for the possibility of existing creatures like us if certain parameters in physics were had different values. But never mind the theistic or other uses that the physicists have in mind. What I want to emphasize is that the kind of modal play that they engage in is intrinsically very interesting and almost certainly not conceptually incoherent. We know it's not conceptually incoherent because it describes our world in incredibly precise detail. it doesn't mean it's the last word in physics that we won't have replacement theories that are slightly different. But at a certain level, we can't doubt that we've got really a hold of extremely important facts about the nature of what exists in our world. And so, although if you just start talking about worlds with where charge behaves very differently, and worlds with things that are completely complicated like X, Y, Z, but they have dispositions that are exactly like those of water, you're putting words together, but you don't know that you're really talking about coherent possibilities. I think that the physicists have much stronger ground. Just to give an example really quickly, this is really not part of the sort of the anthropic and fine-tuning literature, but King and some other physicists did a widely cited study looking at how water's relevant chemical features would change if we played with fine structure constant and this parameter beta, which is the mass of the electron to the proton, the ratio of those two masses. And the details here don't matter. Here we're looking at play with the fine structure constant by making alpha 0 is the value in our world, and see what happens if you increase the fine structure constant. What does that do to the angle at which the hydrogen molecules hang off of the oxygen atom in water? And you can see that they have various different ways of calculating it. It gives you different results, but in general, the angle gets lower as you increase the fine structure constant. And that would rather quickly around here make the chemistry of water very, very different. Over here, what they're looking at is the distance separation, as it were, between the hydrogen and the oxygen in water molecules, which goes up as you get as you play with this ratio of electron and proton masses. And that again is significant for the chemistry. In particular, they say that if the angle gets too small, then the tetrahedral symmetry or approximate symmetry of water would be lost. And then water would not anymore be less dense when it freezes than liquid water is. And that fact is apparently extraordinarily important to the way water functions in living beings. But again, it doesn't matter whether you care about what happens to life in these sort of circumstances. The point is, the physicists know how to play with things and think about how the chemistry of water could be different, but it would still be water. These are still worlds with hydrogen and oxygen, the familiar atoms. Absolutely no question about that. So to take stock of the second part of my talk, physics gives us a framework allowing constrained modal speculations that are anchored in mathematical calculations and known possibility. And by contrast, the disposition and powers literature, it seems to me, offers us just a framework anchored in non-mathematical language, permitting unconstrained speculation. Well, it's restrained by grammar and shared intuitions, but those constraints don't make for that much progress. And I just want to say one caveat, though, about this. I'm trying to criticize this literature brutally, but I want to admit that my criticism here is directed at doing this towards basically the fundamental physical laws in our world. It may not be so inappropriate to bring back Aristotelian language and talk about capacities and powers and so forth in other sciences, higher level sciences like economics or biology and stuff like that. So I'm not trying to be an across the board anti-Aristotelian. Okay, to wrap up the talk. What I've tried to argue is that Kripke and Putnam did show us that some essence claims are actually true. And so there are a posteriori necessary truths that are quite interesting. But these are perhaps less metaphysically deep and more partly, not fully, but partly about how humans use language than Kripke might have originally hoped. I've tried to argue that the embedding of their insight in the sort of a framework, which is a hangover of logical positivism, causes problems and leads to confusions. And from the second part of the talk, the moral I want to draw is a slogan from my former teacher at Stanford, Pat Suppies. Philosophy of science, or here philosophy of nature, should use mathematics and not meta-mathematics. And well, with that, I'll stop. Thanks.
Take a 2-minute break for questions, then we'll have a 2-minute break, then we'll have plenty of time for questions.